So we are ready. When you want, and when yours arrives, you can start. Okay.
Hi, it's Alexander. I'm Jordi, the other technician of IT. Nice to meet you. ¿Se ve bien? Everything is correct? Yes? Okay, perfect. Vale, okay. Ready. Son dos cosas de las diferentes sitios. Yes. Pero no, eso sería. Esto sí, entonces, buscar bien. ¿Qué vas mirando? Vas a fácil. Este había sido el subdirector de Cerda. Sí. Sí, no está aquí. Porque está aquí de lado. Sí, está bien hacer las cosas. Y este también, este es el conductor de vaso. Y el bazado está por aquí también. 72. No tomarla. Se puede ir a la curioso. Bueno. Para ser así, pero pues no se dejan poner en
Hi everyone, welcome to the lecture of today. Today we finish off the notion about finite chain rings. What is the finite chain rings? What is the finite chain rings? A is a finite chain ring if A is finite local ring and its maximal integer is principal. Okay. Uh, Note that finite chain ring is finite local principal integer ring. Okay. For example, ZP power A is a finite chain ring. Is finite chain ring. Is finite chain ring. You give the algebra structure of finite chain ring. Let A be a finite chain ring with maximal integer M. We have the version singleton 0 equal M power S. Sigma content is M power S minus 1 dash 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 S dash 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 A, where S power T equal theta power T A for all T between 0 and 0 and and S. Here, theta belongs to M. Theta is the element of M. Theta is not of M square. And S is the more or less integers. Is the more or less integers, positive integers, such that M power K equal singleton theta. For example, if R equal ZP power A, P est prima A est positive integer, M égale P A. M égale P A. We have this chain singleton 0 égale P power A. P power A segment content is P power A minus 1A. Segment content dash 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 segment content PR. PR is the maximal integer of this ring, this example ring. Segment contenu in A. Okay. Okay. The final chain ring is the final local principal integer ring. So for that, we have coefficient ring. Let A be a final chain ring with coefficient ring R0. That is the Galois ring. Okay. And theta is a generator of the maximal integer of R. Then A égale R0 theta. Here, there are three parameters, P et A. We search two other parameters of the final chain ring. Fourth parameter is given by this chain. But P is here. PR is an integer of ring R. And and this chain dash 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 PR dash 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 P R dash 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 PR. This chain allowed me to write this. There exist k in non-negative integer such that theta power k equal pu, where u is a unit of the ring R. K is the first parameter of the chain ring. K is the parameter of chain ring. A last parameter is S. S is the nilpotence index of R. Any finite chain ring has 5 parameters. PARKS. Okay, you continues. The aim is to write a finite chain rings as extensions of the Galois is the coefficient ring. You see the theta periodic representation, theta adic representations of elements of R. R is the finite chain ring with maximum index generated by theta. Okay. Propositions. For all x in R, there exists a unique x0 in Teschnuller set such that x equal x0 plus theta q0, where for some q0 belong to R. Okay. We recall that gamma R is the set of elements of R satisfying these equations. Q is the number element of residue field where FQ is the residue field, of R. Okay. This is a tabular set. Okay, this proposition allow me to write periodic representation of elements. To rewrite this, is the sample. Is very same. Okay, you write the proposition here. You write again proposition here. Propositions for all x, there exists a unique x0 such that x minus x0 belong to M. M is equal theta R. M is the maximum integer of R. Okay, you take x, you can prove x0 plus theta Q0. Theta is the element of R. Continuous. Theta can write x1 plus theta Q1. Continuous. X0 plus theta x1 plus theta square. Q1 can be write as x2 plus xq. We will exclude plus theta q3. You continuous dash 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 continuous you x0 theta x1 plus theta square x2 plus dash 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 plus theta x minus theta power x minus 1 x. Okay. Since theta x equal 0, this is okay. This is good here. Okay. This is the p-adic, theta-adic representations of x. Okay. Of x. Okay. X is a unit if and only if x0 is different of 0 of R. Okay, this is the consequence. This is the consequence of the data periodic representations. Okay, it continues. we can prove theta power k égale pi u, where u is the unit of R. Thus, then u equals PID representation of u equal t go to 0, t go from 0 to s minus 1 u ut theta power t with u0 different of 0 because u is the unit. Theta k times sum of t go to 0 goes 0 to s minus 1 ut theta power t. Okay. Ut is element of R and u0 different of 0. Okay. We organize this sum, we obtained theta k égale pi somme de somme de I goes 0 to k minus 1 et 0 et I theta I. Okay. Don't forget this theta power k égale pi u, where u is the unit of the ring R. You use this equality to organize this sum. You obtain this last sum. This last sum means that theta is the rod, is a rod. Theta is a rod of the polynomial gx égale k power x power k minus sum I goes 0 to k minus 1 a 0 x power I, where ai belongs to coefficient ring of R, A and A0 different of A0, sorry, A0 is unit of Galois ring, Okay, coefficient ring of the R. Okay, this polynomial is called Eisenstein polynomial. Eisenstein polynomial. We see that in arithmetic number theory. This polynomial. Okay. This polynomial, all coefficient A0 belong to Galois coefficient, and constant term is I forget important. Yeah, P. I forget this. Okay. A0 is the element of the R0, and AI belong to R0. Okay. Theta is the root of the Eisenstein polynomial. Theta, which is the generator of the maximal integer, is a root of x power s and jx, where jx x power k minus b sum I goes 0, k minus 1 is 0, x power, where which is 0 is unit of Galois ring. AI is 0. Okay. Okay, this means that R equal jx. This means that you write this means that theta power s equals 0, because theta is root of this. Theta, j theta equals 0. This means that theta, we can write theta as x plus this integer, theta j s. Okay. When we obtain these polynomial representations of the finite chain ring. Okay. Finally, finite chain ring, we can write Galois coefficients, Galois coefficient G x. Okay. X. Okay. For example, you take Euh, OK. Hmm, X power 5. This is the final chain ring. Here, Jx equal and S equal 5. The parameter of this ring is 9. 9 is 3 square. Is the parameter P, A, R, K, S. P here is 3. A is 2. R is 1. The rank is the Galois ring of 1. K. K is degree of the Einstein polynomial. K is 3. S is nilpotent index in this nilpotent index of ring. K is 5. Okay. You recall that the cardinality of financial ring equal Q power S. Q is the cardinality of reduced field, and S is the nilpotent index. In this case, R has 3 power 5 element. Okay. To finish with this lesson by construction of the final chain ring. Okay. We take the construction of Galois rings. We can construct this where alpha and if is a primitive polynomial over Fp of degree R. Okay. Uh, we, we, uh, we go to SearchMate. We have the program to, okay, primitive polynomial. Okay, this is the program. Okay, P, for example, we take 3 degree. We construct the final field of cardinality 2 power A. P is 2. Is 2. Degree is 8. Okay. I take the time. Oh, sorry. Yeah, my, I take a small degree. Take a time. So, okay. À viens of the cours, enseigne this segment. Sorry. To begin with lesson 3. Program doesn't work. Oui. Okay. Okay, today. Okay, sorry. Okay. Galois range of degree R. Okay, beta is the root. Beta is the root. D is the lift of F. Is the lift of F. Donc D is a basic is the basic primitive polynomial over Z P A of degree R. D is the Helsel lift. G is the Helsel lift of F. For int with lesson 2, we remark this Helsel lift. Helsel lift Okay, yeah. We say that F is the left Helsel lift of D to R if PF equal G, F divides X power n minus 1 in Rx for some positive integer n. Theorem. G has a Helsel lift to Rx if and only if PG is square free and G and constant term of G is different of 0. And Helsel lift of D is unique. Okay, this meant that we hire technical. Okay, P is net is the ring epimorphism. Is the ring epimorphism. Okay, we extend these applications to polynomial. These applications is a ring epimorphism. A ring epimorphism. c'est subjectif. OK. Hessel leaves mean that use these notations. D, we dRx of x. OK. Power A. This is the element of Rx such that D is monic. We take order H. H is monic. H divides this polynomial -1 -1. Okay. Okay, this, the set of the monic divisor of this polynomial. Okay, we define this D, Q, the set of the polynomial the set of this polynomial such that H is monic and okay, H is monic, and here bar H is FQ. FQ is that the set of divisor H is monic. No, H bar is the P of H. Technically, Helsel say that P of this application and this set to this set F send PF is bijective. For any D, for any D, for any D, there exists a unique F such that PF equal D. Okay. For all D, for all D, for all G, for all G is a polynomial over Q, such that D divine and G is monic. There exists a unique F in Rx such that such that PF equal D, when that F is the lift of D, and F divine X power Q R minus 1 minus 1. Okay, that is the Hell cell lift. That is the Hell cell lift. Okay, Hell cell lift. Donc, for any D over FQ, there exists F over R such that the F is the lift of D, and F divine X power Q power R minus 1 minus 1. R is the degree of F. Okay, let us continue with a lesson 3. Lesson 3 is, where's lesson 3? Okay, lesson 3. Lesson 3, final Frobenius ring. Final Frobenius ring is the structure of the final Frobenius ring is the limit structure for the construction of the correcting code over ring. Okay. This lecture gives the structure of the Frobenius ring, algebraic structure. Okay. A motivation behind using final Frobenius ring. The character of module had are for any final Frobenius ring are admits a generating character leading to identity. This identity, when you run a linear algebra, we have this identity. We call this identity in linear algebra. Linear algebra. E is a vector space over field F. Dimension of E over F is final. Okay. For any subspace of E, we have a dimension of F plus dimension of joule F equal dimension of vector space equal à E. Okay. This relation, if a final, we have then joule of F is also final. We have equal okay, equal E equal cardinality of E. That is cardinality of F power N. He called that this meant that E is homomorphic to F. N is dimension of E over F. Okay, we have these relations when you are in a vector space of finite dimension. When you replace F by the ring, this relation is not a true for the Sun ring. Is the true if and only if a ring is the Frobenius. That is a motivation of this section. Okay. This equality is true if the ring R is Frobenius. Okay, what is a Frobenius ring? Okay. Our objective of lecture 3, we establish Chinese remember theorem for finite ring and characterize finite Frobenius rings. Chinese remember theorem say that any finite chain rings is right as the direct product of finite local rings. That is the main result of this lecture. We call a concept of module of ring. Let R be a finite ring. An abelian additive group M is an R module if there is an operations R times M to M such that we have distributive, you have a left distributive by this element of R. Second, you have the right distributive by element of M. Third, we have the mixed associativity. Okay, let one can be viewed as the identity to left. When we replace R by the field, we obtain the vector space. For example, Rn can be viewed as the R module for any positive integer. Maximal integers of the ring, if M is the maximal integer of the ring R, then residue field can be viewed as the R module. We explain that R is a finite. R is a finite ring, and M is a maximal integer of R. Okay. Rm is an R module. It's an R module. Is enough to define operation. Operation is R than R X associate P A X. P is this map, canonic map. A associate A plus M. Okay. This operation, these operations with okay. Residue field with operation is an R module. We can check it. Can check it. Okay. We recall that a submodule of the module M if N is the subgroup of the group R plus, and for any A of R and any U of N, product AU belongs to N. Finally, integer of the ring of the R module. The integer of the ring can be viewed as the R module. Okay, yeah, this is a natural consequence of definition of the submodule. Okay. The structure theorem of finite rings. Let the R be a finite ring and M1 dash 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 M2 is maximal integers of R. Then Ri power A plus Rj power B equal R. Means that Ri power A and Rj power B are coprime. Check of the proof. If A equal B equal 1, then Ri is script content is this sum. But Ri is maximal. That implies that the sum of this module of these integers equal R by definitions of maximal integer. To prove for any A and B, enough to compute x plus xi plus sd power A plus B. Xi belongs to maximal integer mi, xj belong to maximal integer mj. When to expand this power, use binomial monom. Use a binomial monom. You obtain this term. The first term, free. The first term, you note that these products belong to Ri power A. Since Ri power Ri, okay, wait, okay. You put in factor Ri power A. This implies that this sum belongs into Ri power A. The same to last sum. This proof that Ri power A and maximal integer mi power A. Integer mi power A and integer mj power B are coprime for any A and B, for any positive integer A and B. Okay, this is first result. Second. Okay, second result. The maximal integer Ri for any I between 1 and u. Maximal integer maximal integer, the power of maximal integer stabilized by the range. You explain that this is consequence that R is the final print. Okay, you explain that. Okay, you explain that. Okay. I sigma I square dash I K. R is finite. Then the number of is integer are finite. Then they exist. EI such that MI equal MI plus 1. Okay. I is different. By this, okay, we write this. For any t greater than ei, we have mi t equal mi power I. Okay. I is a stational, I is the is a stability index. I is called a stability index of mi. We prove that mi power ei is different of singleton zero. Since maximal, since we prove that for any A and any B, any A and any B, sum of this integer equal R. This implies that AI power EI is non-zero integer. Second, AI AJ equal AI intersection with AJ. Sketch of the proof. We obviously MIMJ is contained in this intersection. Inverse, this inverse is coprime. In plus, this is a consequence, this intersection is consequence that this inverse is coprime. Okay. Second, free result. This quotient ring is local. This quotient ring is local. Is local. Maximal integer ring is here. Okay, it's local. This is only maximal integer is this ring because mi is unique maximal integer of I contained this integer. It continues. A radical of a ring of the ring R is the intersection of all the maximal integer of R. Use consequence intersection of two maximal integer equal product of this maximal integer. Use radical of R power A equal M1 power A intersection MU power A. This okay. Radical integer system intersection of all maximal integer. Power A power A intersection of power intersection of maximal integer power A. Okay. R is a finite ring. M1 dash dash mu is maximal integers, and E is global maximal. E is the global stability index of R. Okay, you explain global maximal. E is the greatest of EI. E between one of you. This is called global stability index. Global stability index of R. E greater than EI for all I. Okay. Okay. We know that the radical of R power E. E is global stability index is equal singleton is null, is zero. We use characterizers of the radical. The radical of the ring equal nil radical of the ring. This equality is satisfies is role if R is the finite ring. Okay. If R is the finite ring, we have this equality. R is the finite ring. We have radical of R equal nil radical of R. Nil radical of R is set of nilpotent element of R. Is set of nilpotent element of R. When the R is finite, there are this equality. Okay, we write this proof at the end of this lesson. When we send me a message if you want this proof, you are send this lesson at the end. Okay, you know that this important result, radical of the ring R power global stability index of R is 0 integer of R. Okay. We finish by proof of the Chinese remember theorem. Let R be a finite ring M1 dash 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 MU is maximal in years. E, the global stability index A. Consider the natural epimorphism. CI is the map. It's the natural map. It's the epimorphism of the ring. CI is a natural map. By theorems, it defines C defines the R from R2 product of direct product of final local ring. This ring homomorphism is injective. We prove, we claim this result. Okay. CI R by this local ring. You know that E power E equal E power this EI is stability index of maximal integer EMI. Okay, E is the global stability index of R. X cent X plus MI power E. C, the map. X associate C1X plus CU E goes 1 to U X. Okay. Is obviously this map is the ring homomorphism. X belongs to kernel of C if and only if for all I between 1 to U, we have CIX equals 0. This means X plus 0 in this ring is maximal integer. Okay, this is continuous for E between N of U F of U okay, U X belong to this integer. Okay, this means that X belong to this intersection. This intersection equal radical of R power E. Okay, donc kernel of C equal radical of R power E. You prove that R power E is 0 in real. Okay, this proof C is the ring monomorphism. Okay, C is the surjective. This is consequence of this result. The integral M1 power E, mu power E is pairwise coprime. In consequence, R égale M1 power E plus -- plus mu power E. This prove C is surjective. Explain that. Explain that. Explain. Okay. C. A. C from A to this direct product of final local ring x and C1x plus CU x. MI E and MIJ are pairwise coprime. This implies that, okay, this means one R can be expressed as R1 plus IU, where RI belongs to MI power E. Okay, if you take Y's, is that Y's belong to this direct product? Y's equal 1 Y's 1 dash Y's U. Okay. How to express a, okay. You can write okay. Okay. You have forget the way. Okay, it's not okay. Tomorrow to prove that you leave this in analysis this then to tomorrow. Okay, you continues. Chinese remember theorem for final ring. You note that every final ring decomposes uniquely up to permutation of factors and isomorphism as a direct product of final local ring. C, the map C is a isomorphism. The map C is isomorphism between between R and direct product of the final local ring. Okay. C, this is isomorphism. We recall that we call reciprocal map of C Chinese remember theorem. Okay. So, R is Chinese remember theorem of R1 dash 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 RU. R1, Ri is a finite local ring. Okay. In this circle of this lecture, we studying sculpture of the final local ring and use the Chinese remember theorem to generalize the result to any final ring. This is the ideal of this. This is the mechanism of this theorem. Okay. Okay, this picture sum up all to say on the Chinese remember theorem for final ring. Let on top final ring R with maximal integer R1 dash 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 Ri dash 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 Ru with global stability index E. We use Ci to obtain final locally. We obtain a final local ring. Donc, to local from global to local, we use Ci. To local, from local to global, you use Chinese remember theorem. Okay. When we have when you work on the final local ring, we can use we can use reduce modulo. We reduce with Canonical map pi to obtain final field. To lift to final local to reduce to final field, and so on. To obtain the final ring by using the Chinese remember theorem. In the circle, you work on the one with final local ring. This picture sum up all to say on Chinese remember theorem. Chinese remember theorem extend to polynomial, to we have Chinese remember theorem for polynomial over final ring. To have Chinese remember theorem for the module for the Rn module. Okay. Annihilator of an integer. Annihilator of an integer is set of the element of S vanish all element of I. We know that the annihilator of the gel is the joule of the gel. We can see of the joule in gel. Okay, when R is the final local ring, we have important theorem of Nakayama say that R is a final R module if maximal integer of ring R, product of maximal integer module R by we repeat, product of maximal integer of ring R by module M equal module M, then we have M is equal singleton 0. We use in this exercise use this theorem to prove I contain annihilator of A. We ask questions. Do we have annihilator and annihilator of A equal A? An annihilator of A equal annihilator of A? Answer is the false. This we take this ring, we compute annihilator of A. We constate we have a difference of I of integer I with annihilator of I. Okay. Okay. R is the Frobenius if quotient ring R by radical of R is isomorphic to circle of R or the R module. The circle of the ring is the sum of all minimal elements. For example, final chain ring is the Frobenius ring. We have lattice of the integers of the final chain ring. The circle, in this integer we have the only minimal integer. This is only minimal integer. This is maximal minimal integer. This ring is local. Therefore we have only maximal integer. The radical of R is the maximal integer. We have quotient ring R by maximal integer equal isomorphism to residual field A result field isomorphic to circle of R. Circle R of the m power s minus 1. S is nilpotence C index of maximal integer. We see that R is a Frobenius ring. It is important to see that the annihilator of maximal integer equal a circle. We have the duality between radical of the final ring and circle. We have a duality. This duality expresses as circle of R equal annihilator of maximal integer. This first example, is a first example. This theorem characterizes Frobenius ring by using Chinese remembered theorem. R is the Frobenius if and only if R1 dash dash RRU are Frobenius, the circle of proof. Ci of radical of R equal radical of I. And Ci of circle of R equals circle of Ri. And use a definition and prove that R is the Frobenius ring if and only if locally Ri are Frobenius ring. In this circle, we work with the final Frobenius local ring. Okay. Important example. Every finite principal integer ring decomposed uniquely as a direct product of the finite chain ring. For corollary, finite principal integer ring are Frobenius because it's the product of finite chain ring. But finite chain ring is a Frobenius ring. For example, we take this example. We take this example. Go to the bar. Explain that. Explain that. Okay. We take R. This is isomorphic to Z4 times Z9 because 4 times 9 equal 36. Okay. Maximal integer of R. This is 2 square, 3 square. Okay. Max M1 equal 2R. M2 equal 3R. This is these are the maximal integer of R. R is the two maximal integer. Okay. Global index. M global index power 2 power 2. Okay. M square equal M1 square equal M1 free. We can prove that. M free equal 2 power 3 R equal 8 power 8 8. Okay. 8 8. How to it can be right place. Okay, stability index of M1 is 2. How to see that? How to see that? How to see that? Okay, we can return to the course, the lecture. Okay. Okay. We use the Bézout lemma say that Bézout lemma okay, Bézout lemma okay. Tomorrow we return this. Tomorrow to return this. We write this example. Bon. Okay. Radical and circle. We prove radical and circle. Maximal integer is 2 for this example. Radical of this R is intersection. This is 6R. Okay. We can view that global maximus is 2. 6 square is 36. 36 is 0. Modulo 36. Okay, circle. Well, this is circle of R. Minimal integer is a sum in minimal integer. Minimal integer, we have 4 times 3, 12, plus 9 times 4, 15. Use a GCD of 12 and 15 equal 12 4 times 3, 15. 2 times 9. GCD 3 times 3R equals 6R. Okay. Puis, so radical of R equals circle of R. Okay. We compute equals circle of R equals circle of R. Okay. R radical of R. How to compute this? 6 equal 6R equal circle of R. Okay, for example, this ring is the Frobenius ring. It's isomorphic to 6. Okay, can compute this. Look, continuous. Okay, this example, we take this ring. R is the F2U, U square equals 0. This is the lattice of the interior of this ring. We observe that maximal interior is generated by 2 and U, and circle is generated by 2U. Circle is the principal interior, generated by only element. We know that here we have this product. Cardinality of maximal interior times cardinality is joule of maximal interior equal cardinality of ring. This ring is the Frobenius, but is non-chain local ring. Is the Frobenius, is the local Frobenius ring, but it has only maximal integers. It's a non-chain ring. Okay. This is example of the Frobenius local ring, but that is a non-chain. Continuous with this example. This is the final local ring, but is not Frobenius ring because radical equal circle. Radical of this ring equal circle. Okay, we compute this. And this, in this, we claim that in the board, in this example, radical of R equals circle of R. With that R radical of R isomorphic to F2. Okay. Different of circle of R. R is not Frobenius, is a not Frobenius ring. Okay, we define, we give a characterization of the final Frobenius local ring by additive character. An additive character of the ring is an group homomorphism. The set of the additive character is called module character. A module character is the R module with the action star action star defined as the follows: R times rat R. Okay, defined by the action star defined by as the follow. Okay. R is the Frobenius if and only if we have this identity. Cardinality of maximal integer times cardinality circle of is equal cardinality of the ring R. Character module of R is isomorphic of R as the R module. Character module is generated by generated by only element. R is the Frobenius if and only if circle of R is a principal integer. We can see, for example, here we have a Frobenius ring. The circle is integer ring. When is a ring is local, of course. Final chain ring is the Frobenius ring. Naturally, obviously, the circle is a principal integer ring. Okay, characterizations of the final local ring. In this, important characterization is the second, 3, 4, and 5. Okay, we note that R is the Frobenius ring if and only if cardinality of the submodule of the subgroup C times cardinality of Joule equal cardinality of R power n for any submodule, for any subgroup C of Rn and for any positive integer n. Okay, this is identity. R is the Frobenius ring if we have this identity. When R is the not Frobenius ring, we have identity is false. This identity is important in coding theory. When we know cardinality of the codes of the linear code C and deduce the cardinality of Joule by this identity. Okay, recall this theorem, fundamental theorem of finite abelian groups. Finite abelian groups is also isomorphic to direct sum of circle group. This fundamental theorem of the finite abelian group we use to obtain this table. This is the local Frobenius ring of order 16. First, the characteristic of this ring is 2. First ring is the field with 16 elements. In this field, we go to bar. In this field, okay, this field is isomorphic to F2 power 4. F2 is the subgroup. F2 is the subgroup. F's can be right where is polynomial is a polynomial basis. When X belong to this field, X can be right this. Can be right this. Okay, x1 alpha, x2 alpha square s3 alpha square. This is the coordinate. Okay. The character. This ring is a Frobenius local ring. Character module is isomorphic. It generated by this character. This character is generated by -1 a plus b. Sorry. Okay. Character is defined by 16c times. Element of this can be right. G associate -1 power a plus b plus c plus d. Okay. Okay. First, additive structure define alone to write the generating character of the character module of R. Second, characteristics of this ring is 2. And additive structure is this. We use it to write the generating character of the Frobenius ring, and so on. Last table, this ring, Galois ring, characteristic of this Galois on this ring is 4. Here 4, 4, 4, 4, 4, 4, 8, 8, 8, and 18. This the additive structure of this ring. The additive structure of this ring allowed us to write the genetic character of the character module of the local Frobenius ring. Okay. The additive structure of additive structure ring has two structure. First, additive structure. Second, multiplicative structure. Additive structure is isomorphic to we can write as direct sum of additive structure is the abelian is the final abelian group. We use fundamental theorem of the final abelian group. We express additive structure or ring as the direct circle group of direct circle group of direct final circle group. Okay. This is the local Frobenius ring of the order 16. As I check that there are no local Frobenius ring of order 16 up to ring isomorphic other than those in previous tables. We have two tables, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, we have 14 local Frobenius ring of order 16. In this last lesson, we use final chain ring. Almost this local Frobenius ring order 16, which is the final chain ring. Well, this is the exercise for tomorrow. First, this is the final field. Final field is the final chain ring. This is the final chain ring. This is the final chain ring. This is a non-chain ring. This is a non-chain ring. Galois ring is a final chain ring, naturally. It's easy to see. This is the final chain ring. This is the here is the non-chain ring. This is the final chain ring, non-chain ring, non-chain ring, non-chain ring, and last is the final chain ring. Okay. You use this table to understand the algebra structure of the final chain ring and generality algebra structure of the final local Frobenius ring. For last lesson, you studying the corrective codes over ring, especially you use final chain ring to index 2 to write the example. To write example, the die is finished. Sorry. And don't compute. I don't use the search math. Tomorrow you see that how to use this to help me to compute the lifting hands, the hands lifting, the hands lifting. The hands lifting important to construct the cycle code. This lesson is finished. I say thanks a lot for your kind attention. Final Frobenius ring an essential work, an essential framework. Now let us to use them to understand and build the structure on some code on those rings. Thank you so much for your kind attentions. See you tomorrow for the last lecture. And write my email to send this lecture free. My email, and recall that. Okay, thank you very much. I send you the program SearchMath. You can use it to compute the Elsa lift and primitive polynomial and basic primitive polynomial. Okay. Thanks a lot for your kind attention. Okay, it's finished. Yes.
Whenever you're ready, we will do the interview.